So I'm going to talk about two recent pieces of work. It's like a concatenation of two talks, and I'm a bit worried that I might have too much material, so I'm going to skip some of those. Tell me, please, if something doesn't make sense. I will try to do a better job. So, little bit of information about me. So I've worked in automatic differentiation for a while. Then I've been doing probabilistic programming during the last 2 or 3 years. And I'm interested in applications of machine learning for scientific problems. Like I work with particle physicists, connecting their simulators to probabilistic programming systems, which is the second part of the talk. And in general, I'm doing things like collaborating with space scientists and astrophysicists, heliophysicists, doing like basic machine learning for tasks they care about solving. And I organized this workshop at NERDS called Deep Learning for Physical Sciences, which we hope to do again this year. So if you have any interest in like submitting this type of work, machine learning for science, please keep an eye on that. So I would like to start by just talking very briefly about automatic differentiation, because I am, I think, kind of known for that. So I'm not going to talk about that in detail today, but I have these like lectures I gave at the University of British Columbia recently. They are 2 automatic differentiation lectures. If people have access to the slides, like they can use these links to check out the lectures. They represent my best effort of explaining what is automatic differentiation and how it's working. So that's that. And as Andrew said, I've been working on this diff-sharp library in F#. So this is like a little slide where I'm trying to make the point that there are lots of automatic differentiation tools, which you can see here. These are industrial strength automatic differentiation tools in fields like scientific computing. And in machine learning, we have like witnessed a lot of machine learning frameworks with automatic differentiation basically appearing. And so this is basically just a little summary of what sort of things are out there. The ones in the bottom are from the machine learning perspective, basically. So in diff-sharp, I basically work with these 2 people, Jeff Siskind and Barak Perlmutter. These are the people who really care about having an automatic differentiation system expressed in a functional programming framework. So with that influence, we picked F# as the language that we work in, and we implemented a system where you have basically everything you can do with automatic differentiation: operator overloading, implementation of automatic differentiation, and you have an API where you have all sorts of like higher order gradients, higher order derivatives available to you, and you can combine these things in F#. Like you can compose any derivative taking operation with any other. If the function signature matches, you can just combine these things, and you can go like up to any depth of differentiation. Yeah, you can do many levels of differentiation. This is what I'm trying to say. And so we are currently revisiting this. I'm working with Tom currently to re-implement the diff# with support for tensors and like trying to modernize it up to like current mainstream frameworks. Basically trying to re-implement it, keeping the API and the higher order differentiation operations, and doing it in a way that will be like useful as a mainstream machine learning implementation framework. So this is like a little, it's not very little actually, list of differentiation operations in diff#. So the point I was trying to make is like this. You see the function signatures for these like higher order operations. These are higher order operations. It means they take functions and return functions. So there's like a Hessian operator. It has this API. It has this function signature. So if you can match this with any other thing in this list, and things just work. So this is something interesting, and it was the basis of this hypergradient descent work I'm going to present immediately after this. So that type of capability gives you like a way of expressing things in a very compact or like pleasing way, in a functional programming way of implementing things. So for example, this is the actual code for in diff sharp for the Hessian. This is like the Hessian operator. It takes a function and then a point at which you evaluate the function. You basically implement it as the Jacobian of the gradient of the function evaluated at x. So this thing works thanks to the underlying implementation of the operator overloaded types. So this ends up doing forward on reverse differentiation internally. And yeah, this is just a variety of the same thing that returns the gradient and the Hessian together. Like this returns a tuple, I think 3 tuple. It returns the original function evaluation, the gradient of it, and the Hessian of it evaluated at the same point. And this thing works with like a simultaneous differentiation of forward and reverse varieties. So the yeah, this is about what sort of things you can write with nested derivatives in diff sharp. For example, here you see, can I use the mouse pointer? No. Yes, I can. This is a bit easier. So here you see this expression implemented in diff sharp in this line. This is basically, you take derivatives with respect to x and y at different points. So the thing that happens here is that you have a free variable reference here in this internal thing. So there's this x here. Internally, you take a derivative with respect to y. So you do that derivative taking expression, and you can have an outer derivative taking expression that takes this derivative of x through that in a correct way. It is not very straightforward to achieve this, so there are some tricks to do that I learned from Barak and Jeff how to do correctly. So they have a whole paper about like how to get this thing right. And Barak has the habit of, for example, when people do new automatic differentiation libraries, he goes in, he tries to write this, and most of the time they fail. He opens a GitHub issue, he says, like, you should read this paper. For example, this thing happened if you are familiar with the Python autograd library implemented by the Harvard people. So it was the basis of the autograd in PyTorch currently. So initially there was a little bug about that, and they quickly fixed that. So it's an interesting thing to consider if you think about like nested derivatives and implementing those. So this is online learning rate adaptation technique that was inspired by this derivative nesting. It was at ICLR last year. So I will try to briefly introduce that. So this is the standard gradient descent update rule. So you have an objective function f, and it is a function of theta, and you have an iterative procedure where you make updates to theta using the derivative of the function of the objective multiplied by the learning rate. So this like a basic gradient descent update rule, and this is how you can write it in diff sharp. And as a recursive function, there are other ways of writing that, of course. So basically, you can have a recursion where at the given point, so this x corresponds to that theta there, s corresponds to t. Like so, maybe I should just start here. So that's your vector to scalar objective function. This is the initial point in the parameter space of that function. This is the learning rate, and this is the number of steps that you run the gradient descent for. And what you do is like you get the gradient at the current location, and this is basically a for loop. If you run out of steps, you return that location. Otherwise, you keep descending by updating x to beat this thing. Like you update x with the gradient multiplied by the learning rate, and you do recursion. So this is basic gradient descent in F sharp, in diff sharp. So the thing I was trying to do is, because I have this nested derivatives available in the system, I'm always looking for like ways of using that, and I was thinking actually like Barak mentions in papers where you can have a gradient using optimization routine, and you can take derivatives through that. right? So you can have a gradient-based optimization algorithm, and you can take the gradient of the gradient optimization algorithm with respect to some of these like hyperparameters. So this was the type of thing I was after. So I was thinking, okay, so this is the gradient of f with respect to theta. This is the standard thing. Can we have something like that? Can we have the partial derivative of this f, like the objective with respect to the learning rate, the scalar learning rate? Then if you had such a thing, you could do updates to the learning rate as well. So you would be doing gradient-based optimization of the learning rate at the same time. So, and this is called the hypergradient. The term hypergradient is introduced by McLaren, Dueno, and Adams in their ICML paper, where they also do some type of gradient-based hyperparameter optimization. But they do something different from what I'm presenting here. They do, like, they have an internal unrolled gradient optimization where you have all the steps in memory. Then you have to backpropagate through these whole steps. Let's say you have like a 100-step running gradient descent run. Then they have a way of keeping the information to be able to reverse that and to backpropagate through the whole internal optimization routine in an unrolled way. Which is different from this because the way I'm doing things is like these. I will end up with an algorithm where you do online updates to theta and alpha in lockstep fashion. They are simultaneous updates. Yeah.
Does f mention alpha?
Sorry?
Does f mention alpha? I'm taking its derivative with respect to alpha, but it doesn't mention alpha. So isn't the derivative always going to be 0?
So it's coming in the next slide. So there is a little.
Yeah. So we can't understand.
Yeah, it's not here. The information for that is not.
How this hypergradient descent works at all.
Yeah, no. So it's, I haven't done the job yet. So this is like, yeah, the way it's currently written is it doesn't have any dependence on alpha. Yes. So what you do is you remember that this theta at the previous time step, it was something that was also the result of the previous update. So you can expand that. So theta t minus 1 was theta t minus 2 updated with the gradient at that point. And this thing involves alpha. So this term, if you look at it, like f depends on theta, which is like a regular thing. It also depends on alpha in this expansion. And you can keep doing that. You can add more terms. But I don't do that, and I just truncate it here.
So it's not df d alpha applied to theta t minus 1. It's d d alpha of the expression f of theta t minus 1.
Could you repeat that? I think, so this t minus 1 here, theta t minus 1, it is this thing.
That whole thing.
Yeah, so it is actually that. Like we want this term, and it is that. So if you take the derivative, so there is a derivation in the paper. There's a whole section. I was really.
I think you just fix it with brackets.
Oh, you mean, okay, so maybe I didn't get the point. So you were saying maybe there's some problem with the notation or something?
I think you would square brackets just before the f and ending after the parenthesis.
All right. Yeah, okay. Yeah, that would work. Okay, I guess. Right. Yeah, I'm going to remember that. Yeah, so that's the little trick you can do. So actually before doing that, I just, so I was doing this like a little experiment in diff sharp. And I ended up doing that. Okay, so even before looking at this type of things, like what's going on. So because I knew that code-wise it's possible to, like if you remember this algorithm, right, the recursion of gradient descent. So I have this alpha. So we take a derivative with respect to x here. This is the initial x. Can we take a derivative with respect to this alpha? So I ended up writing it in a form in diff sharp that supports that. So you still have the gradient of f with respect to x. This represents that. So this diff operator in diff sharp is like it's equivalent to grad actually. It's just called diff because the forward version of grad is called diff. Maybe I should rename that. So I'm taking a forward derivative of a function. A represents alpha, like function of learning rate. So given any alpha, you start by computing this gradient. You think that you make an update with the current gradient, right? So you make this update to x, you evaluated f at that point, you get the gradient. So it corresponds to this thing there, I guess.
So GG corresponds to that.
Yeah.
T minus 2 minus alpha blah.
Yes, I think with this part, like the gradient part of it.
Okay.
Yeah. And yeah, so then you return the value of the function, the objective function, after another update with that gradient. So this, I think this one corresponds to that one. Like this one corresponds to the theta t minus 1 part, and this one is the preceding one. So you write this function, like this is like taking an alpha and giving you an objective value, internally doing the gradient update of with respect to theta, but it returns the, you write it in a way that depends on alpha, so that you can use take a derivative of the internal derivative taken routine with respect to alpha, and you evaluate that at the point of alpha. It's a bit maybe confusing, but we could write it in better ways. Andrew had some suggestions about like making it more readable. I think I was just trying to make the point that you can write it in 10 lines or something. So basically, the recursion is very similar. So you make an update to theta, or x in this case. You also make simultaneously you also make an update to the learning rate using the derivative with respect to alpha. So this is how it works. So I saw that this was working in diff sharp, so I did that. Oh, sorry.
So here's some code. You probably run it.
Yeah.
Is there any reason to suppose that adjusting alpha in this way is going to be an improvement for gradient descent algorithms?
Yes.
Why do you think that?
So people do like learning rate adaptation. Like it's a field, like people in the optimization community, they have all sorts of techniques for adjusting the learning rate as you do the gradient descent. Like there are many techniques. So I was thinking, what if we use gradient-based optimization of the learning rate? There are papers about that, like from 2000, for example. Yoshua Benji has a paper. He talks about the possibility of doing that. Maybe he doesn't do that. I don't remember exactly.
Okay, so
yeah,
you're
so
not
it's
giving
like
an intuition for why it might be a good thing. You're just saying other people think it might be a good thing, and I can implement it.
I think I was just looking for ways of like making use of this nested derivatives that's available in the system. That was my motivation.
Okay.
Then I ended up like writing this, seeing the possibility that it works. So it works. So when I say it works, so for example, this one here, this is an MNIST training with a simple feed-forward neural network. So the top one is the learning rate evolution. So here it's a function of epochs. This is the training loss, and this is the validation loss. So I don't want to maybe spend too much time, but so the behavior of learning rate, and like you can look at the paper and the poster. So you can start alpha from 0. That works also surprisingly. So alpha 0 can be 0. You can start with a zero learning rate. This rule is enough, like has enough information to push it up from 0 to some useful value. Like it goes to some useful level. It does some job of training. Then it starts decaying spontaneously. It has this decaying behavior, and it decays around 0 and fluctuates around it. So this behavior comes out of the system. And in the paper, we do a better job of explaining that. But so I will come to the maybe anticlimactic or underwhelming part. So this thing was working in diff sharp, and I started sitting like writing the equations to see what is really going on, like this forward derivative, the reverse derivative, what is really going on behind the scenes, like what is being like executed in the code. So when you look at that and when you try to take the derivative yourself, like using basic calculus, basically. So you can write it in this way. So the derivative, if you do this like, if you do this replacement of that with this and take this derivative, you end up with an equation. This is basically an analytical expression for the derivative of the objective with respect to the learning rate. It's basically the current gradient, the dot product of the current gradient with the gradient preceding that. So if you just keep this in memory, always like keep an extra copy of the gradient and do the dot product between that, you don't even need the forward diff. That's what you end up with. And this thing applies to basically all gradient-based optimization routines. Like we have, so for example, in this figure, I have normal SGD. I have SGD with Nesterov, Adam. So it is possible to get this sort of, basically just do this dot product and get a gradient with respect to alpha. And this also works for per parameter learning rates. Like instead of having a scalar alpha, you can have a vector of alphas. And it just works by doing this as an element-wise product instead of a dot product. It just gives you the correct thing. So this is what is explained in this paper. So the summary,
Instead of writing the code you showed on the previous slide,
Yeah.
there's lots of very clever things behind
Yeah.
the scenes.
it
You
turned
do
out to be
2 lines of mathematics
exactly.
and do something even simpler than code
Yes.
that is much more efficient as well.
Yes.
Okay.
So this
No need to be sharp then, just do the maths.
in this case, yes. So it's exactly that. Like this, the morale of the story is like this is enough. You don't need all that extra machinery in crazy functional language.
So you made yourself redundant.
Yeah. So
Well,
this also,
the
sorry.
benefit of that formula is that it answers Simon's question about intuitiveness, because that
Yes.
formula is actually very intuitive. for
Yes,
solving that.
exactly. People notice that. So so you can interpret that as like.
Insufficiently educated.
So people working in optimization, they immediately notice like what this can be interpreted as. Like you have, like it tells you, have I changed direction, or am I going in the same direction, or like how things are going. Like, so there's a heuristic value here. People actually come up with this sort of rules and incorporate them into the algorithm. But the interesting story here is like this I didn't engineer that. It just fell out of the chain rule of calculus, and it's working and it's doing something useful. That's like what is
So if you
happening.
expanded one more layer to
Yeah.
t minus 3,
Yeah.
what was the formula you'd get?
I haven't done that. So I leave it as an exercise. Yeah. Sorry?
It would only take 5 minutes to do.
Oh, yeah.
Cool.
Yeah.
And then maybe
So
you get
let's
more.
spend the next 5 minutes doing that. We can do that.
LBFGS too.
That sounds interesting, yeah.
There are interesting things. Like actually, I mentioned this type of things in the paper. There is also the possibility. So there is also there is something a bit crazier than this. It's not here in the slide. Maybe I'm wasting too much time. Oh my god. So you can also So there is an ugly part here. There is this beta here. So that's the learning rate for learning your learning rate.
Mhm.
So people ask like, what did you gain by doing all of that if you again have a learning rate that you cannot optimize? Like you have to pick that. The short answer to that is it doesn't really matter so much. It's not the behavior here is not very sensitive to the value of beta. It's like you end up picking a very small number, like suggested by us in the paper, like the Adam beta 1, beta 2, for people who are familiar with it. So there is a whole section in the paper explaining that. So there is the possibility of writing a similar rule for beta, like you can take a gradient of this with respect to beta, and it ends up again a dot product of previous gradients comfortably. And you can do that for many levels. You could do like, you can do a gamma, you can go all the way through the Greek alphabet, and you can keep going, and you can, so I was imagining, I haven't tested that. I tested this up to 6 levels. It was working without like diverging or exploding or something. It's not in the paper, but it's mentioned in the end. So I'm thinking maybe someone can like have a master learning rate at the top, which is like maybe what is the IEEE smallest floating point value. Then you can have like a tower of these hypergradient learning rates optimizing each other. So that's like a little idea that I'm not currently pursuing, please. Yeah.
So you're saying you could expand it
Yeah.
depth-wise by
Yeah.
doing beta
Yeah.
gamma.
Yeah, and
And
conveniently,
you
it's
could
again
expand
this
it
type of,
width-wise by having more terms.
Yeah.
And who knows which would be better.
yeah,
They've now got a big square matrix of things to explore.
exactly.
Okay.
Yeah.
Cool.
Don, you were,
I still don't get a feeling for how much difference it made in terms of performance. Could you just say roughly? I mean, in fact, I don't know what the different lines mean on the right. But just some quick summary of what.
you mean like between doing it this way and doing it with the,
With hypergradient descent turned on versus just having a fixed.
you mean,
fixed
okay, yeah,
training.
there are comparisons in the paper. So this is about like, we present this as a learning rate tuning technique. So for example, so there are plots here. So this is with logistic regression. I also things like very big convnet, like VGGNet trained on CFAR or whatever. So it keeps like, so the point is like, maybe I'm using too much time. So the dashed lines here, they are cases of like untuned learning rates that you can pick for this problem. And the solid lines, they are all at the bottom, are the behavior you get like in the loss evolution by using this adaptive learning updates. So wherever you start from, like for this one, there's a corresponding solid red line here. It is here. So the point we are making better in the paper is that wherever you start from, like this thing can tune your thing towards the best possible behavior you can achieve by tuning it in otherwise, like using other types of hyperparameter optimization.
So what you're saying is, in the same colours,
Yeah.
the solid lines are well below the dotted lines.
Yes.
And the solid lines are what you get by adding hypergradient.
Yes. Yeah. And starting from different initial learning rates. So these are showing these things. Yeah. So maybe I should just keep going faster. So this is like a little extension or application of this to model agnostic meta learning. There's this thing called MEML. Some people are excited about this. So there is some bi-level optimization going in the MEML algorithm, and there was a way of like making an extension to the MEML algorithm by doing like hypergradient updates to the both learning rates in MEML for people who are interested in that. This is a very new workshop paper. It appeared on arXiv, I think, last week or 2 weeks ago. So this is where I come to the probabilistic programming part. So this is basically what I've been working on for the last 2 years, I guess. So I was working with Frank Foot. Frank is a very well-known person in the prop community. So the thing I've been focusing on is, actually I will just talk about that, but the thing I've been working on is using simulators, like people's existing simulators as probabilistic programs. So I have an infrastructure doing something like that. So this part of the talk is about that. And these slides are from a talk where the audience was particle physicists, so it has some extra stuff. So I will just maybe skip some of these. But so this is an introduction to probabilistic programming. In probabilistic programming, you define a probabilistic model. You have random variables, and some of them are observable, some of them are latent. Then you can have different classes of probabilistic models. You can have graphical models, probabilistic graphical models, such as this one here. You can have different varieties of this. You can have directed conditioning or undirected relationships or whatever. So the thing you do is like you express a joint distribution of some random variables. You factorize that, for example, for this graph, probability of x, probability of y, probability of z given x and y, because there's this conditional dependence. So what's happening in probabilistic programming is you can use a regular programming language to express probability models. And this is Andy's paper here. Everybody cites that for introducing these constructs. So basically, you introduce two things in a programming language, general purpose, Turing-complete programming language. You have a sampling operation. You make random number draws from a given distribution. That seems easy, but the thing is, what is happening is like you also do some bookkeeping about what was sampled, what was it sampling from, where was the sampling happening. You do some bookkeeping in order to be able to do inference later on. And there is also a condition construct. This is most of the time called observe, which enables you to express conditioning of random variables. Like you can specify that this random variable had this value. What is the distribution of the rest of the random variables to satisfy that constraint? So that's my attempt at explaining prop. Another way of looking at this is, so in an ordinary program, you have some sort of input mapped to an output. So it's going in the forward direction or going to the bottom here for some reason. And in a probabilistic program, you can still have this capability, like you have the program. But using this conditioning and inference, you can do things like, you can basically think that you can invert this program by saying conditioning on some output being observed. What is the distribution over the inputs that can give you such an output? And you do that with Bayesian inference. So this is the whole probabilistic programming framework. And in probabilistic programming, you are just providing the user a language that they can use freely to express like probability models, and they don't have to care ideally about how will I get my posteriors over these latents. Like you just tell them the system does that for you. We have these inference engines in the system. There are a variety of inference engines, and this is to say that the model writing is decoupled from inference. So you just write the model, then you select the inference engine, You give it an observation, and it gives you some posterior over your latents. So this is like a little list of probabilistic programming languages. And what is happening lately is like there's this deep probabilistic programming type of things happening, where you have some deep learning based component helping with the inference part. And this like Pyro and TensorFlow probability are the main libraries of that sort. So what I've been working on specifically is I have a way of, I introduced the framework to execute existing stochastic simulators as probabilistic programs. This is happening for the first time, to the best of my knowledge. The thing in the pro community is they say, okay, we implemented this very nice probabilistic programming language. You just go learn how to use it, implement some models in it, do inference, solve your problems. But people have to implement things from scratch. Like you really have to sit down and write the whole model or whatever you want to do in that system. So what I'm doing is, if you have an existing stochastic simulator with some random sampling happening inside, we have a way of taking that and connecting that to the probabilistic programming system and treating that as a probabilistic program, even when the initial implementation wasn't with that purpose.
Are you going to tell us a bit more what you have in mind by an existing simulator?
Yes, existing, like any stochastic simulator in existence.
That's a certain class of computer programs, but
yeah.
not Microsoft Word, for example. So exactly what class is it? Or are you going to tell us? Maybe?
So there is this term universal probabilistic programming in probabilistic programming community. That means this type of, so for example, I had this little example here. If you do this in a Turing complete language, like basically general purpose programming language, you have some sampling and like conditioning happening, and you can have loops, recursion, everything allowed. It's not like probabilistic graphical models. It's like an open-ended program where you have some stochasticity. Like some examples would be like, I don't know, people in computer vision, they have renderers. Or in particle physics, I work with particle physicists. They have the standard model implemented as a giant C++ simulator where you have a particle coming in and decaying into other particles. They do lots of random sampling for simulating something like that. Or, I don't know, like industrial settings have simulators, like car companies have motor simulators. I don't know, any sort of simulator, like modeling a physical system in code. Like that's what the simulator is in my mind. And the thing is, like these simulators, they already, like if they have some stochasticity, and most interesting simulators are stochastic in nature. Every time you run them, something happens, like something different. They are already probabilistic models, but they are not written as such. Like they are waiting to be executed as probabilistic programs. This is like the thing we are trying to enable. So actually, this is that slide where I say, so if you have a stochastic simulator, so if you remember from Andy's paper, like you need to have sampling, you need to have conditioning. The stochastic simulators already do the sampling. They have a random number generator. They take samples from random number generator. The sampling part is satisfied. So if we have a way of like plugging there and acting as the random number generator, we can treat these things as samples from prior distributions. So that satisfies that part of probabilistic programming. And if you also introduce a conditioning construct that the simulator can use, or like you can run the simulator and you can say, inside the simulator there was this random variable, and I want the condition on that random variable having this value. It is something easy to do once you have this like connection to the random number generator. Basically, we introduced the conditioning construct and we intercept the calls to the random number generator. We provide the interface for that. And this enables us to treat an existing simulator code base as a probabilistic program, basically, for the first time in proper community. Yeah.
So just to clarify, say this car simulator, and one part of the simulation includes sort of dealing with some rare events, some component breaks down,
Yeah.
and sort of the probability of those events by nature is fairly low.
Yeah.
Would your system actually help sort of biasing the sampling towards sort of towards the rare event, and we'll be able to compile all of this bias later on.
Exactly. This is one of the things in the later on I talk about this type of things. Yes. Yeah. So this is like the basic idea. You do Bayesian inference in an existing simulator code base, and you can get like conditioned on some events. You can get posterior distributions over all the randomness in the simulator. Like depending on the size of your simulator, this is a very costly thing to do, and depending on the inference engine. So let's go to that part. The advantages is like there is like a huge collection of existing simulators. So I work with the physicists. There is a reason for that. Physicists have models. They have actually the best model in the history of humankind. This is the standard model. I mean, this is shortcomings, but like they really trust that model. They have that thing implemented as a 1 million line C++ model. It is called Sherpa. There are other libraries doing the same. So in my main project right now, I'm working with particle physicists who implement a particle physics simulation of a particle decaying. It's a tau lepton decay. Actually, I will come to that part later. So the thing I'm trying to say is you can make use of like these simulators that have been developed by domain experts over many decades, and they represent the current best understanding of what's going on in a system. So we make that subject to probabilistic programming, and we can do inference in these simulators instead of using these as black boxes. The standard thing people do in like trying to connect these things to machine learning is like you take the simulator as a black box, you run it many times, you construct a training set of input-output pairs. You can train things from it. You can do like a deep learning system, which can predict things. Like you can invert the simulator that way. You can do like given an output, what would be the input, or you can do even things like Bayesian deep learning, where you get distributions in your predictions, but they are not really convincing to scientists or like these people who really care about like correctness of the results under the model or interpretability or explainability of like your predictions. They don't really like saying, okay, the neural network tells you this is your result. That doesn't work. In our case, we don't treat the simulator as a black box because the simulator remains a part of the inference engine. I will try to explain how that works. Anything you present as a result is an actual simulator run, where you see everything that's happening in the simulator, or actual distributions over this. So the idea is like we provide interpretable posteriors over things modeled in the simulator. And for doing something like this, you need three pieces. So basically, I implemented a new probabilistic programming language with simulator control in mind. And I implemented this thing called PPX, Probabilistic Programming Execution Protocol. This is something like in deep learning, they have the ONNX or ONNX. What's that protocol? It's not a protocol. It's like a serialization format where you exchange neural networks between major frameworks. So this is an analog of that for the probabilistic programming community, where you can connect the probabilistic programming model in a language to an inference engine in another language. So it acts like a bridge of like connecting the models to inference engines. So actually I will explain these things better. And there's a little piece I implemented in the C++ side because the particle physics simulator I've been working on is in C++. So I will briefly explain how these things work. So this is a library currently in development. It's like a alpha or beta quality software right now. It's based on PyTorch and Python. So it has this sort of inference engines available. So I have a MCMC engine, like specific variety for probabilistic programs. So which is guaranteed to give you correct samples from the posterior. We use that as a reference. And we have some important sampling variety called inference computation. And this is basically learning a proposal distribution, like training and proposal distribution for an important sampling scheme using samples from the simulator. So it's basically learning a guide network in Pyro, or like for people who are familiar with that. Like it's basically learning an inference network with data sampled from your simulator and from which you take proposals at inference time. Maybe let's just skip this because I have a better version of this. So this is one way of explaining what's going on. So this is the simulator, the thing here. So there are some addresses in the simulator. Addresses are unique labels for stochasticity in the simulator. So wherever the simulator takes a random number from the random number generator, you have a way of identifying that uniquely, that type of random number. And this is based on concatenated stack traces, for those who care about the detail. So basically, in many simulators, there is a file where you have a random number generator implemented. For example, in the particle physics setting, in that simulator, there is a single file where you have an external RNG interface already in place because they programmed it that way. Like they support plug-in and third-party random number generators into the simulator. So we go there, we play the part of a random number generator, we catch all the draws from the random number generator. From the simulator's perspective, everything stays the same. You don't modify the simulator; it just keeps drawing random numbers. We supply the random numbers. For in this instance, in this example, these are supposed to represent continuous uniform priors. So the simulator requests a random number from this distribution. You supply that. Okay, so maybe we shouldn't look at that yet. So through our interface, actually I can go to the other one, this one. This is how it works in practice. So I have this PPX protocol, which is based on flat buffers. It's like a protobuf type of thing where you can have different ends implemented in different programming languages. So this one is the simulator. So we have an endless loop where your simulator is ready to go as soon as you get the signal from the probabilistic programming system telling you to start simulating. Okay, so this thing represents one forward run, one single forward run from start to end. And these A1, A2, A3 represent the addresses of random number draws. So the thing that is happening is the probabilistic programming system, like, okay, it decides to execute the simulator once. It sends over the protocol like a message saying, like, start or call. Like, this thing is like a remote procedure call or something like that. You make a call, a lot of things happen, then you return the call result. And inside that, the simulator, if it chooses to do so, it can request random numbers. Again, that thing goes through the protocol, and the probabilistic programming system sees that, okay, the simulator wants a sample from a Poisson or uniform or Gaussian or whatever the prior happens to be here. It records that, it does the bookkeeping that we will use for many purposes. It returns the sampled value. The simulator is happy it got its sample, and it doesn't know what's going on behind the scenes. It's just sampling from the random number generator. So you keep doing that. And there is also a way of designating after the fact some of these as observed statements. Like at inference time, you can designate any of the random variables as an observable and put the constraint of this random variable having some sort of value. This is how it works. So these execute like this. So you keep running the simulator and you keep recording traces. So this is how it works in practice. And another way of showing this, one of our collaborators, Kyle, he really likes this way of explaining it. It's like a puppet master. The probabilistic programming system is controlling the simulator in a way to make it do things. Like if you have an observation where you have a particle event, like in a particle physics detector, you observe something, then you have a simulator capable of producing such a simulated observation. You control it in such a way, like every random number draw can be guided in an intelligent way to produce that type of observation. This is how we talk about like the probabilistic programming system controlling the simulator execution by just interfacing at points of stochasticity. That's that type of thing. And maybe the last thing I could say is, so you can do many types of inference engines in such a system. One of them is this neural network-based inference compilation thing where we learn a recurrent neural network. So basically, let's say you have this sort of setup where you run the simulator. You have some sort of simulated output. So you can do that many times. You can run this millions of times, and you will have like x and y pairs, like all x's, all sampled values in the simulator, and all y's like corresponding to each realization of this x sequence, which is open-ended, by the way. It's unbounded because it's a Turing complete thing. Like this thing can be anything. It's not fixed length, and their order can change. Anything is possible. So you just have a recording of all x's and all y's. In this instance, there's just one observable y. So you train a neural network with millions of such executions. You basically sample data from the model, where you invert things, and you put the observable as the input to a neural network through some sort of embedding. In this case, in particle physics, we have a three-dimensional voxel of particle physics detector. We pass that through a three-dimensional convolutional neural net. And we have some extra stuff here that tells the neural network where we are in the simulator. Like what was the previous sample value and where are we in the simulator. There are like address embeddings that basically bridge the execution space in the simulator's execution to some embedding of that the neural net can learn to use if it's useful. So basically you have a recurrent neural network. For a given address, it can give you proposal distributions. The output of the neural network is a proposal distribution. In this case, we use a mixture of Gaussians here. For this example, like the priors are continuous uniforms. The proposals are Gaussian mixtures. And here I'm trying to say, like, given an observation, the neural net, based on its experience of having seen millions of samples, it knows, okay, this type of thing is probably by sampling something around this area. Like it knows that it has some memory of what sort of things can produce this sort of observable. It can be like a multimodal thing, which I'm trying to show here. Basically, the neural net learns a very complicated proposal distribution structure that can work with any execution of the simulator. So the orders and everything can change. Okay, and the way we are training this is KL between the true posterior and the proposal. So as you train it more, the proposal distribution approaches the true posterior, and if you write things down, it corresponds to sampling things from the simulator joint, like the joint prior, and just maximizing the likelihood of the sampled x's under the proposal distribution. So this thing works. This is what we do in the paper.
Can I ask you a question?
Yes.
So you've got this, as it were, C++ program running, and it's talking through this protocol to
yes.
the probabilistic engine. When you do so I understand about sampling, you can ask the probability engine, give me a random number from a suitable distribution. When you do the observations, in the example you gave, you might say, what do you say, observe of C1 or C2, say? Well, so it's important that the engine gets to know that it's the disjunction of C1 and C2. It's no good if you say observe false.
I mean, you can observe.
So, your C++ language is going to compute some, it's going to do lots of work and compute a value that it gives to observe.
Yeah.
But somehow, doesn't the engine need to know how that value was computed, how it depends on the values that were sampled?
Actually, the observations are a part of the inference side, like the inference engine knows the observations. So let's say, so in practice, this works. Actually, they are all samples, okay? So I can tell you, actually, if people are familiar with the way Pyro is doing things, it's also something like that. So by default, you have sample statements, okay? Sample statement defines a random variable. There's some sort of random variable with an assigned prior or likelihood or whatever. So you can keep recording these things, and to your inference, you can give the constraint that one of these things will have a fixed value. An observation means you sampled something from a distribution, and that sampled value happened to be the observed thing. This is how I see it. So you can constrain things after the fact, like you can execute this. In practice, in importance sampling, what we do is like we run this many, many times. And we have the observation constraint available in the inference engine. So you can think about it as like rejection sampling, for example. Like that would be the worst thing to do. But you can think about like discarding all the executions where that condition was not satisfied. Then the remaining things will be representing samples from the posterior where your condition happens.
I think Simon's saying, I understand that the simulator contains calls to round.
Yes.
Yeah.
I don't believe it contains any calls to any other functions.
No, it
names
doesn't.
Like
Yeah.
observe.
So in practice, it means the simulator doesn't do the conditioning. You do the conditioning. So you interact with the probabilistic programming system. You just couple the simulator to the system. Then you just work with the probabilistic programming system. And there are like methods saying, give me a sample from prior, give me a sample from posterior. And this give me a sample from posterior method takes an argument which says, I want a posterior where this address, like A3, has this value. So this is how the observation goes in. And the inference engine in the probabilistic programming side takes care of like running the simulator many times and giving you cases where this condition was satisfied. Does that help? I hope.
No, I'm lost, but we'll talk to you afterwards maybe.
Yeah, we can.
I'm not sure I'm going to get unlost.
Yeah.
Can you simulate real numbers in that case? You couldn't get an exact floating point value.
Yeah, rejection sampling wouldn't work for something like that. So
Okay.
yes, that would be a very bad. So there are different classes of inference engines that work with different things. So we end up having an importance sampling inference engine where you assign an importance weight to each executed trace. So then you do weighting of you do basically weighting of many executions where you downplay ones that don't satisfy it. Like there is some smoothness that is coming with something like that. Yeah, I should go faster. So this is the way you do things from C++. Let's go. So I will just maybe in a couple of minutes finish by saying, so we work with these people, the particle physicists. It's like a fairly large collaboration in machine learning standards. It's a tiny collaboration in particle physics standards. We run things in a supercomputer because for the MCMC part, the simulator is so big, we need like thousands of cores to get the correct posterior to establish that this neural network learns the things from the correct posterior. Okay, so this is a very interesting extra thing to mention. So I will just skip all these things. So someone asked the question related to that. I think he disappeared. So in a complicated simulator, there's like a rare event type of thing. Like in particle physics, for example, they are interested in things happening in the far tail of a crazy distribution. That's where you look for new particles and things. So there are practical issues like handling these things in the system. One is prior inflation. I don't think I have time for it, but like quickly, if you have a prior that looks like this is a categorical prior. In training the neural net, you just treat it as an uninformative, like all things possible prior, like equally probable. You train the neural net with that. It learns like this way, it keeps seeing samples of rare events that it wouldn't see normally. It learns that. Then when you do the importance weighting, you do importance weighting using the correct model prior. Then that works. Basically, the neural net sees things that are not going to, the neural net learns to see a variety of things. Then you have a way of correctly weighting these so that you give samples from the correct posterior. That's like a very bad little summary. Another thing is like how to handle rejection sampling loops. We could also talk about that, but I'm afraid I don't have time. So the experiment part is like we have a particle physics decay case. This is like a logarithmic scale of prior probabilities of decay events. So this is how addresses look like in C++. They are concatenations of stack traces starting from the initial like forward call all the way like up to the RNG sample. You can see that's like somebody wanted a Boolean sample. Is that Bool? No, it's like a normal continuous uniform. And it's the first instance of this continuous uniform. There is a categorical sample. So this is how you uniquely identify locations of random number generator calls in the simulator. And the neural net learns these labels as embeddings of these labels to propose correct things for them. And like I will just go quickly. So this is a prior. Like this is some subset of the things in the prior. This is a posterior given an observation. These are ground truth values. And this is a posterior from like 7 million samples from the MCMC engine that we have like to establish correctness of the neural network based one. So this thing is slow because it's like a sequential thing. And it runs maybe, actually I think this result was for running for 4 or 5 days or something like that. And yeah, I have too many things. So the way we establish the correctness of that posterior is that we do 2 MCMC runs, starting from different locations. If you run them long enough, they converge to the same thing. And there are ways of measuring if that happens, like the Gellman-Rubin diagnostic or autocorrelation or whatever. So you can statistically establish that you have the correct posterior coming from the MCMC. Then I also make the point that the simulator is so big that you have like actually unbounded number of addresses. Like for a given event, like you have thousands of latent posteriors, and we are just showing some that are interesting in the physics point of view, like the momenta particle decay, final state particle energy joint or whatever. But the thing is, like, you get the posterior over the whole simulator. So this is something interesting. And this is the part where I show some neural net results. So this IC refers to inference compilation, the neural network proposed importance sampling. So here you see the proposals, like given this the same observation that we use for MCMC, and we got this for 7 million MCMC samples. So the neural network proposes this sort of stuff, okay? This is before importance weighting. It's already like doing a good job, like proposing, maybe this is from this channel, or like it has an understanding of how to explain that. You do importance weighting, and the posterior becomes that. Basically, the posterior is this thing, importance weighted by the log probability of the traces, and this thing matches that. And you can do that, like for, in this instance, it's like 25 times faster. But we submitted the paper, it's under review, where we have like things hundreds or thousands of times faster than the MCMC case. So this is for making the system useful in practice, like in this type of applications. You don't have to wait days for getting your results. If you have, another thing is like this is parallel. So in an importance sampling inference, you can run many copies and pool the results. If you have compute budget, you can get results faster. So I think I will just finish with this. Because you have access to these trace recordings, you can also things like you can plot like which address is followed by which address, which is like what are the cycles. When you go to this address, do you come back? What is the proportion of times you come back to this? You do that, like you have a picture of what is happening inside the simulator in the probabilistic nodes. And these are corresponding to addresses. And by taking more and more trace samples, you have like a more fine-grained picture of the simulator appearing in your like library that you are capable of seeing, like inspecting or introspecting what's happening in the simulator as a probabilistic model. So these things are falling out of the system. Yeah, we should just conclude. I think it's already concluded. Yeah. So I'm working on this type of things, and let's conclude there, I guess.
Thank you.
All right. That's a bit too much, right? Okay, all right.
Some people may have to leave.
Yeah, sorry about that.
Was the current adoption of PPX?
So there are a couple of PhD students, they are doing the same with the malaria model, epidemiology modeling. There is one doing computer vision. It's adopted within the lab currently because it's a very new thing. So it's supposed to be like a properly documented library so that people can use it and connect it to other systems. For example, I have my own probabilistic programming system, but I was talking with the people doing Edward, for example. One could imagine making a bridge from PPX to Edward, PPX to Pyro, like, and they wouldn't have to do the part we already did. We connected this particle physics simulator to the protocol. That part is done. You can connect that to Pyro and try to do some inference in Pyro, for example. So I want to make that like a properly useful library. Yeah, but not yet.
So how are these big simulators used today, like before PyProp exists? What
They
do
do
use?
things manually in particle physics. Surprisingly, they don't do like very Bayesian things. They are not actually okay with that. They are always disturbed by talking about priors and things, but where does the prior come from? But in astrophysics, for example, they are very okay with Bayesian things. Particle physicists, they have this simulator. They say it should be somewhere in this region. They define some regions for parameters. They run things. They do histograms. They inspect histograms. It's a very manual thing currently.
It's kind of sampling.
Yeah.
They just run lots of simulations.
Yeah. So we kind of automate that, I guess. Yeah.
So you're basically automating that
Yeah,
process.
yeah.
So, go on. Right.
Okay.
Anyone else?
No? Okay.
All right,
Thank you.
yeah, okay, yeah. Thank you. Yeah, no time for questions.
Okay.